Okay, shall we begin? So, the previous session, we had some idea about certain etiquettes and manners, as we call, when we enter a lab. A culture of a lab, that you should not be satisfied with something told to you, but you should spend some time about the procedure. Why is it the way it has been carried out? Why there is a particular instrument that I have been given, right? So this is something that we dealt with, right? Was it too fast? Too slow? Feeling sleepy? No? Good. Ready for the next session? Sure, right? Thank you. Okay. Okay. So a very important topic, right? Uncertainty analysis. Let's try to understand what it is. Okay. I think till now in your colleges you have been dealing with this topic as error analysis. Am I right? Yeah. I mean, we hardly term it as uncertainty analysis, right? But let's try to understand what is the reason behind calling this topic as uncertainty. Let's do that now. Okay. So how many of you calculate uncertainty in physics experiment? I think some of you have already raised your hands, right? How many of you don't calculate that? Just raise your hands. That's perfectly fine. I just need to know how many of you don't calculate error. Oh, all of you do that. Great. That makes my life easy. How many of you take care of this in daily life? Is the question clear? Now I have come out of the lab, right? Daily life. Do you take care of error analysis? Do you think about certain aspects of error analysis? No? Sure? Let me give you an example. I can make a nice tea, by the way. I have not chosen this example because you are girls, no, or women. So don't stamp that gender bias thing now. How many of you do not know how to make a tea? That's perfectly fine. At least you can make a coffee, right? Okay. When you want to boil water for tea, right? Will the water boil in 3 minutes? Are you sure it will boil in 3 minutes? What are the assumptions? What are the assumptions? Exactly, that's what I'm trying to understand. What does it depend on? Amount of water, then, yeah, the flame, right? Low, medium, high, right? What else? Yes, very nice. Which part of India are you doing this tea? Right? In fact, yeah, we had a problem when we sent one experiment throughout the country for some competition. The same experiment, when it went to Delhi and then it went to some place like Madurai, right? We asked students to note down the fall of temperature starting with 80 degree. And then we realized in Delhi, even if that water is boiling there on one corner of the table, to get that boiling water to the table, by the time you start measurement, it has gone to 75. Right? So it actually also depends on what is your ambient temperature, what is the initial temperature of your water, right? All those things, right? So all these factors are going to give rise to uncertainty. But now tell me one thing, you are at your home, right? You are doing this every day, maybe 7 a.m. in the morning for your parents or somebody, right? Every day, right? You know there are 3 people in your house, right? You know how much tea they drink. Things will be standardized in terms of your water amount, right? The flame, right? At what point of time, you are going to switch that flame from high to medium, right? So all these are standardized. In that scenario, you can even say it can be 3 minutes plus minus something, a 1 minute or a half a minute, right? So you do think about this kind of a range, okay? based on so many parameters, but you keep all other parameters perfectly same because now you have standardized the procedure of making a tea. Right? Even in experiment, after doing so many things, say simple pendulum, you have standardized things. Right? When your teachers give you the apparatus, it's like, it's not that for you they have made a special apparatus. No, right? It's the same thread, it's the same bob, it's the same instrument that you are using. So with all those things same, what is the change, what is the range in the final answer that can be achieved, which depends on your skills, right? So you do think about this error analysis even in daily life. How much time do you take, to reach from your house to your college, right? There are so many parameters. But if you do this daily, plus minus, 5 मिनट तो देरी हो जाती है, कभी कभी 5 मिनट जल्दी पहुंचते हैं, right? That kind of a thing. So we are aware of this analysis since we were born, maybe, right? Okay. This is some interesting thing that I observed in Iran. Don't worry about all the geopolitical situations, but in last year when we went to Iran for International Physics Olympiad, in one of the restaurants we found those bottles. Can you notice something on the bottle? We don't find such bottles in India, right? Plus minus 12, plus minus, and look at this, plus minus. Surprising. I mean, I did not actually open it and measure it because, then I had to open so many bottles and drink them. But it's such a inspiring thing that even their industry is so much, vigilant about, okay, if I give you a certain product, it might have something like plus minus. Right? We don't actually here bother about that. We just open the can and then drink it. That's all, right? But it was interesting. That's why I just took a photograph, right? Okay. So why calculate uncertainty, right? The knowledge about measured quantity is useful only when the uncertainty in its magnitude is stated. For example, if I tell you that this table is strong, right? How strong? Is it that it will not break if I stand on it? It will not break if an elephant stands on it? How strong? But if I tell you that it has a load bearing capacity of 10 ton, then there is some number associated with that, right? 10 ton plus minus how much, right? So if I specify that range, I know, yes. So the moment I specify uncertainty, that quantity becomes more meaningful, right? For example, experimental results published and it becomes a public property, right? If you own a pharmaceutical company and you come up with a particular drug, some medicine, right? Are you aware of this curve? Yeah, normal distribution, right? So 1 sigma means the area this much, 68%, right? Can I say that my drug or that medicine that I have come up with is okay with 1 sigma? No, it will apply to 68% of the population. Is it okay? No, right? I hope no. If you are okay with it, don't open a pharmaceutical company, please. Right? Okay. 2 sigma, 95%. Still not good because you are dealing with population, not a very small sample. Right? 4 sigma, 6 sigma. So most of the companies work with 6 sigma levels. For example, this is basically, this 6 sigma was kind of a brainchild of this Motorola. They started implementing it and they found that their profit actually, went to around 17 billion or something like that. They saved 17 billion by implementing that, right? Trying to be as perfect as possible, reducing all these variations to a minimal level, right? So there are companies which are like, certain examples where they really, I don't want to talk about this right now, but no, it's not fine. We do laugh about it, but whatever has happened is pretty bad, right? But this is something, kind of a data that I have got, but unfortunately what has happened right now, but let's forget that right now. But then this is something that these are like 6 sigma idea is quite followed over there. Right? So you come up with any such thing and then You convince people that yes, my product is so good. And to convince them, you have to specify at what level you are working. Right? Okay. If you design a device, right? For example, digital multimeter. You have been using a digital multimeter, all of you, right? Anybody in your college, did you, when you got a digital multimeter, a brand new digital multimeter, did you open the box? You may not have got the chance to do that, right? But did you see there is a box in which the multimeter comes in? No. Multimeter का box भी नहीं देखा कभी? Okay, fine. But then obviously when they give you a multimeter in the market, they just don't give you a multimeter. They pack it in a nice box and give it to you. And along with that box, you have a small manual, right? So the uncertainty, which is actually written or which is expected in any of the range, in not just the least count of that range. For example, if you're using a 20 volt range on a digital multimeter, a 3.5 digital multimeter, right? The maximum that you can measure is 19.99 volt. 3.5 digit. Why do they call it 3.5 digit? 1, 2, 3, and this is half. Right? So when you have 3.5 digit multimeter, which are the multimeters that you are using, you do get 5.5, you do get 7.5 digit multimeters, but they are mostly expensive. Okay. So generally in the market, 3.5 digit multimeters are pretty common. So in this case, generally we say 0.01 volt is the least count. Okay, so the last digit, you cannot have that 7 segment display. It's just half. You cannot get 2 in that case. Just half of that is displayed. So this is the half thing. If it's 5.5, then you have 1, 2, 3, 4, 5 and half. You can also get 4.5. So depends. It's just the cost is more because, okay. So what I was trying to tell you that if this is the reading, normally we take 0.01 volt as the least count of the thing and we go ahead with this is the uncertainty involved in that, right? But there are manuals that come along with this. Don't get scared by those numbers, right? I'll just pick up one range, maybe in DC voltage, go for 20 volt range as the same thing, like this 20 volt range, right? So what you do, this is like plus minus. That plus is gone in the photocopying or something, right? So this is plus minus 0.8% of the reading, plus minus 1 digit. That 1 digit nothing but least count, 0.01, right? So whatever reading that I get, I should take 0.8% of that and then add 0.1 or 0.01 volts in that. Where does this number come from? This is a digital multimeter, right? Whenever I measure a certain voltage, what do I measure? Do I measure a digital thing or do I measure an analog thing? Analog, right? It's an analog signal, right, that I'm measuring. That gets converted into digital, A to D converter, right? There is something like analog to digital converters available. How do you measure that? How do you do that? There is some kind of a slicing done, right? Sampling done in that. Better the sampling, higher the cost of the multimeter, and lower is this value. Right? So this is your normal market wala multimeter, which is like plus minus 0.8%. But if you go for a better version of multimeters, this value will be lesser because the A to D converters that they use are of better quality. Right? So whenever you come up with any digital instrument, there is a manual that comes up with it. A good quality, a good quality instrument, right? Even digital thermometers, right? They also code those values, right? What is that uncertain in that, right? So if you are making an instrument, you are coming up with some product, you should specify what is the value of that, right? Okay. If you are testing something, have you seen this website, NIST? It gives you a list of different constants measured, right? I'll just show you one such sheet, right? So for example, look at the Newtonian constant of gravitation. Can you see 6.67430 into bracket 15? What do you mean by into bracket 15? Those last 2 digits are uncertain by 15, plus minus 15, right? So every constant when they measure, because this is a measured one, right? But at the same time, you look at Planck's constant. You're saying exact. How is that possible? How is that possible? No, no uncertainty at all. Are you aware of this whole story of defining 1 kg or say mass in terms of Planck's constant? Do you know how 1 kg is defined? Can I call this 1 kg? Am I 1 kg? Certainly not. Right? I also ate a biscuit, right? I'm certainly not 1 kg. So how do you know that certain thing is 1 kg? You need to have a standard. Right? You need to have a standard. There was a standard for so many years. There's a platinum iridium cylinder kept somewhere in Paris, right? That was the standard, right? Of certain shape, right? But then there was a problem. I'll show you a video. Have a look at that video. Okay? And how many of you know Veritasium? So many of you know Veritasium and you don't know about this video. My God, I'll just show you. I hope the sound plays fine.
On November 16th, representatives from nearly 60 nations will be meeting in Versailles, France, to vote to change the definition of a kilogram. Not only that, they will also be changing the fundamental unit of temperature, the Kelvin, the unit for amount of substance, the mole, and the unit for electric current, the ampere. That is 4 of the 7 base SI units in one day. And after that, all SI units will be based on fundamental constants of nature and not physical artifacts.
Sorry for the lag.
The kilogram is the last base SI unit to be defined by a physical object. Since 1799, 1 kilogram has been defined as exactly the mass of a single metal cylinder stored in Paris. It was swapped out once in 1889. But this international prototype kilogram, or Big K as it's affectionately known, has problems. I mean, weighing it with, in theory, identical cylinders, scientists have found that their masses are diverging, so it doesn't even seem to maintain its mass. Plus, it's really hard to get access to Big K, and that makes using this definition really difficult. So how do you create a mass standard that will never change and also be available to everyone, everywhere? Well, the solution is you set Planck's constant to have a fixed, exact value. Now, I know that sounds a little strange, so bear with me for a moment. I mean, Planck's constant is best known for relating the frequency of a photon, a particle of light, to its energy. But we also know that energy and mass are related through E equals mc squared. So hopefully you can see how Planck's constant is involved in mass. But the problem, as it stands today, as I'm recording this video, is that Planck's constant has some uncertainty. I mean, we know the value of Planck's constant to a large number of decimal places, but those last couple of digits, they're actually uncertain. What is certain is the mass of that platinum iridium cylinder stored in a climate-controlled vault in a basement in Paris. It is exactly 1 kilogram, no uncertainty. So the solution is to flip this on its head. Set Planck's constant to have an exact fixed value, and then that cylinder in Paris will no longer be exactly 1 kilogram. I mean, it'll be a kilogram, but not exactly. The thing that is now exact is Planck's constant, which determines how big a kilogram is. But if you're gonna fix the value of Planck's constant, well, you better get that value right so that it's consistent with all of our current measurements and all of the masses that exist in the world right now. And so for the last several years, scientists around the world have used multiple different techniques to try to measure Planck's constant as accurately as they possibly can. One of the major methods was using a watt balance, where essentially they balance the weight of a kilogram with the force from an electromagnet. If you want more detail, you should check out my video on that topic. Scientists also created arguably the roundest object in the world, made of one type of silicon atoms. These methods have been complementary because now they're able to compare all of their different findings from physics and from this more chemistry method of Avogadro's constant and determine what Planck's constant really should be. So if the vote goes well, the future definition of Planck's constant will be that it is exactly this number. Planck's constant is fixed. That cylinder in Paris, no longer exactly equal to a kilogram.
Got it? So it's basically the advancement in your instrumentation, how well you can do that, as well as you have another method to compare that. And then you come up with a value of H, right, which is very much exact to a particular decimal place, which are tolerable for you for different mass measurements that you can carry out. Right? That is the meaning of exact. Right? So in all such cases, obviously, you need to understand what an uncertainty is. Is that clear? Yeah? Okay, fine. Of course. Okay, so now what he is trying to ask is like, they have said that this is exact, this is the value and there is no uncertainty. When you try to measure, obviously there has to be some uncertainty, but beyond those decimal places, right? So if you need a certain kind of a field in which you really need so much of decimal places to be used, obviously you have to quote it with that. So what he is also trying to say is the same thing. Yeah, to all your practical applications, this is perfect. Okay, so this is a bureau which has been thinking about this uncertainty problem for many years, right? Let me just show you a paragraph from this book, which is like free to download. And it is a big kind of a book that you can have a look at. But more than that, there is another book, which is this by Stephanie Bell, which is a very small leaflet kind of a thing. Again, free to download. Of course, when we set up this Google Classroom, I can upload both these literature on the classroom. So maybe somebody can help me to do that. So just like to read this paragraph. In 1977, recognizing the lack of international consensus on the expression of uncertainty in measurement, the world's highest authority, this CIPM, requested BIPM to address the problem in conjunction with the national standards laboratories and to make a recommendation. Right? So things have been going since like 1977. Right? It's not very recent, but the document that I'm going to share is quite recent. Right? So they have been really thinking quite a lot on how does one define uncertainty in different areas of science. Right? Different applications. So this is basically their job, and they have come up with a booklet of that, right? Okay, fine. Okay. From international, let's come back. Okay, here. So our knowledge of a physical quantity is inadequate unless we know how to measure it, right? Our knowledge about the magnitude measure is inadequate unless we know what is the uncertainty in that measurement. So theoretically, a physical quantity can have an exact magnitude, but measurement can never claim to give an exact magnitude. But of course, you know, when you write what exact in front of Planck's constant, what is the logic behind that, right? So these are the three words, right? Mistakes, error, uncertainty, right? Mistakes we all know, right? You are measuring period of oscillations, right? Maybe for 10 oscillations. Just by mistake, you measured for 11 or measured for 9. That's a mistake, right? She was somewhere there, somebody was mentioning about the parallax error. Yeah, she was mentioning about parallax. It's a mistake, right? So now once mistake is done, we are clear with it. Let's try to understand what this error and uncertainty is all about. So what is our intention? Intention of measurement is determination of true value. What is the true value of a variable? What is the true value of the length of this table, this from here to here? I need to measure that. But before I ask you to measure length of the table, measure length of this pencil. How much is it? 11? Yeah? Everyone agrees? 11 centimeter? I expand it. Is it really 11? No. What have I done? I have given you an instrument with a better least count. Right? So instead of a scale, if I give you a vernier caliper, right, I will go up to second decimal place, right? So I might have something like maybe 10.97 or something like that. Good. Then I give you another vernier caliper with 0.001 centimeter least count. You will have one more decimal place. And this is how, if I go on giving you better and better instruments, I will all the time will get a better value, right? So what I do is I end up measuring the best value. I will never know what the true value is. I will never know what the true value is. Like for example, you assume G to be 9.8. Are you sure it's 9.8 here? No. Then you use simple pendulum to get value of G. Do you think simple pendulum is a good experiment to get value of G? You may not know, but let me tell you, it's not a very good experiment, right? Then you go to bar pendulum. You know those pendulum with holes, then you put those things and then oscillate, right? That one, right? Better than simple pendulum, but still not a very good thing. And then you go to Ketter's pendulum. Okay, the process of measuring G with Ketter's pendulum is so good that you really get beautiful values of G using Ketter's pendulum, right? And, I mean, there's a reason why people started with simple, then went to this bar pendulum, then went to this Ketter's pendulum. The method improved, and then you started getting better and better value of G. But every time, nobody knew what is the true value of G. Okay? You could know, better value of G up to certain decimal places. But still, tomorrow you give a better one, you will have better value in that. Right? Okay. So the idea here is the difference between the true value of the quantity being measured and the measured value is called error. Right? That is how they define BIP. Since we do not know the true value of the quantity, we will never know what the error is. What we know is only the best value, which depends on factors like least count of the instrument and measurement procedures adopted. Right? So our job is to find by what magnitude is our best value uncertain. And that's uncertainty in the measurement. Right? So now people are no longer using this word error, right? But they are using this word uncertainty because they have clearly differentiated. For example, in different pendulum experiments, you do this when you write your conclusions, you do this in your journals, that G from calculation, G from measurement, right? Or say by graph. Then you take mean of that. Then you assume G to be 9.8. Then 9.8 minus that value divided by 9.8. Because you assume that 9.8 is the value, standard value at that place. Who knows? I don't know that, right? So there are different ways in calculating uncertainty in experiment. You cannot just assume that this is the particular value of that variable. Okay. So what are the types of uncertainties? There are two effects that can give rise to uncertainties, right? That's all. That's all. All your human, instrumental, everything falls under these two categories, either there or there. So what is random uncertainty? Which happens randomly. And what is systematic? Which happens systematically. So simple. Definition is very simple, right? Let's try to understand this random thing now. Okay. So repeating the measurement gives randomly different results. T1, T2, T3. Right? Which is beyond your control. Beyond your control. Right? Tomorrow I give you a wire, a steel wire, with a screw gauge. Right? And your teachers keep telling you that you measure it at least at 10 places on that wire to get average diameter. I hope so. Yeah. No? Or they do? Or you have never done? Never done? I mean, if you have not done this, measuring diameter of a wire with a screw gauge. Oh, everybody has done that. Great. Are you now feeling sleepy after coffee? Or getting bored? Sure? Or are you tired? Or you getting bored?
No.
Ah.
I have not done.
Oh, you have not done. I thought, no, he raised his hand like, getting bored. Yes. Okay, fine. Okay. The idea is, if you have not done, that's fine. If you have a steel wire right? Just imagine a steel wire and a screw gauge. At least you have handled screw gauge. Anybody who has not handled screw gauge, please tell me. Thank you so much. Okay. How do you handle a screw gauge? Suppose this is a screw gauge. Then, and there is a wire here, right? How do you do that? Turn that, turn that, turn that. It comes and touches it. Keep turning it. Keep turning it. You know? अच्छे से पकड़ो. We do that, right? We just forget that there is something here. बेचारा शांति से बैठा है. Right? Your teachers tell you that tuck, 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 that's enough. है ना? But we don't follow that. I mean, अच्छे से पकड़ना चाहिए. The problem is that because of which you might get variation over the whole length of the wire. That is one reason. Another reason is the manufacturer of that steel wire is least concerned about the experiment that you are going to carry out. Right? He just made that wire for some other purpose. So while drawing that wire, drawing means not drawing that wire, right? They were not very careful about the tension. Right? It might be, sometimes it might be a loose one or it might be a tight one. So you may not have same diameter throughout the length of that wire. So there are so many such parameters. You might get a random variation in that, right? So if you do it multiple times, what will happen? The statistics will help you. Average will give you to the best possible value. If you still go for more measurements, you will still have better value, right? Okay. Fine. So simple pendulum you all know, T1, T2, T3, right? Okay. So a small sample size is going to increase the uncertainty of the equations being drawn. So if you just do it for two, maybe T1 and T2, not a good practice to do it, right? So you do it multiple times and you can get a better estimate of the value of time. Right? So by having a large sample, the impact of random uncertainty is diluted. Right? Let's try to have small activity. Do you have water in the bottles with you? Right? You will need water. What I'm going to do is I'm going to give you syringes, small syringes. Right? You are going to find out diameter of a single water drop, considering that drop to be spherical. Right? How you do it is your problem. So I'm not going to discuss the procedure, but I think how many are there right now? 72 exactly. Okay. So maybe 3 students with 1 syringe should be okay. If you are still left with more syringes, we can just give it away. I got something like 30, 32 syringes maybe. You can start doing it, don't wait. But just keep your notebooks aside. So final answer is not important to me. Okay. Final answer is not important to me. But your procedure is important to me. So you decide your procedure and tell me what you're going to do. Is yeah. No.
Tomorrow also very important. The first session tomorrow will be major exercise in use of computer. these rules are already few people were.
I hope everybody has got the syringes on which markings are very much visible. Right? You didn't get. Just join some group. Vibhor, do we have some syringes? We have? Or do we have some syringes? At the end. I mean, I would require some help from the volunteers whenever. I mean, you should thank Vibhor to come to your place and given it. Sorry. Tomorrow you can just plug it in from there so that nobody falls. Yeah. Okay. I know that, but
the volume which one drop comes out and 4/3 pi r cube.
but this is the only apparatus that you have, nothing more than that. This is the only apparatus. No. But you have some markings on that. Maybe in a minute or so, I will start discussing the possible ways in which people are doing it. Not yet.
Taken it approximately to 1 ml, 1 ml.
1 ml.
1
Okay.
ml. We put a drop.
Hmm.
So the volume is slightly reduced.
Slightly. Okay.
Yeah. The change in volume is taken to be the volume of the water.
Okay. Good.
And from there 4/3 pi r.
Very good.
From there,
Procedure is right, but there is something missing in this. Just one drop.
1 drop.
You have just taken one drop. That's all. Enough. I don't know. Anything? Any luck?
The volume
Of?
water which will take in the syringe. That volume is related to like if we consider it as perfect then
Yeah, but then where is the water? Oh, how did you calculate?
volume.
How much? 1 ml? But there is no water. But will that be same? Suppose if I today give you water and then tomorrow I give you surface tension, I mean the soap water. So these calculations will not matter to me. I mean, it's like you may not have the same value for drop for both. So you'll have to actually do it to see it. Tell me. No, but how many drops did you take? Just one? I just showed you a slide just before this, so I'll come.
Assume it how we will do that the process.
So the first step, we calculate the volume of the fluid and just if it is a spherical.
So according to the formula, if we take 0.05 ml, then we can do R cube. And by the process is R is equal to cube root of 0.05 into 3/4 pi. We can do like that. Then we can get the R value.
From the volume.
Will that be same for all the solutions in the world? Now I have given you water. Tomorrow if I give you soap solution, will it be same? Coming, just a moment. How many drops?
One.
I showed you some slide just before this. Just single drop. Think about it. Yeah, somebody.
1 ml. And then we measure the total drops of
Number
of
Yeah.
drops divided that by
How many drops did you get?
25 and 26.
Okay,
26 actually.
26 actually, or 25 actually.
26. 26. 1 ml. So each drop will be.
Your method is perfect, but you did it only once. Yes.
So for 1 ml, how many number of drops? 4 by 3 pi r cube into 22. So we got 22 drops that way. And then we divided.
Are you sure next time you do it, it will be only 22 drops? Your method is correct, but you have done it only once. Right? So repeating the result is that. Okay, can we? Okay. Won't that be a small sample value for calculating your R? I mean, don't you think if it's like you go for a larger volume, the number of drops will be larger? So your value that you will be getting will be a better one. So if your sample size is larger, you will get a better value. Just with 1 or 2 drops, you might land up in trouble. Right? Okay. Yeah, you have to. But then the number of drops that you count will be more and multiple times. I will just explain that. Okay, let's discuss now. Most of you have been trying it. Actually, some of you have been just calculating it, right? And assuming that this should be the, if I just change the volume by 1 ml, right? 1 ml water comes out, right? Then considering that as a thing, okay, I will just take it as a 4 by 3 pi r cube and get R. The problem is, if I take water, okay, and then if I take soap solution, will the value be same? So you'll have to actually do it in 1 ml, how many drops are falling. Just by doing calculations will not give you the answer, right? That is one. Secondly, most of you started with either 1 drop or 2 drops, right? I just mentioned in my previous slide, larger the sample, better will be your value, right? So some people started doing it with 1 ml syringe, water coming out, number of drops formed were around 26 or something for them. Some place I got 22 or something, right? Syringe is same. How can you get 22 and 26? So one needs to verify it once again. Those who got 22, they should try it again. Those who got 26, they should also try it again. If you do it 3 times, then you should be in a position to tell convincingly, no, it is 26 for my syringe. Right? Lastly, I'm really not interested in the final answer of what is the radius of that or diameter of that thing. Okay. Lastly, the variation that you should be getting, right? Maybe you do it once, you may do it twice, you may do it thrice, right? The way in which you press the piston also matters a lot. In which region? If you fill that syringe completely, and the syringe is exactly at one end of that thing, right? A piston exactly at one end of the syringe, then you might find a bit of a difficulty in pressing it. Similarly, if you're at another extreme, okay, a small amount of water there, again you will have some difficulty in pressing the piston. So the better way to do will be the intermediate 1 ml, right, wherein you can go very slowly. While pressing also, how should you press it? Slowly, so that that whole drop gets its own time to form and then fall. If you dhad karke ho gaya, then in some cases you might be taking that extra water in that and it will just fall. So you may not be getting the correct volume of that water, right? So a very simple activity, but it tells you about the sample size, the technique, right? And then the complete methodology that you can adopt. Is that clear? Yeah? Okay, let's go ahead. So random uncertainty you can take care of, but then there are so many such parameters that you have to really think about. Systematic. Somebody was asking me, what all types of systematic uncertainties are there? You have some question? Yeah. Here, no? I just explained that. You take intermediate 1 ml, right? And then press piston so slowly that the water drop forms very slowly and then falls down. So for 1 ml, how many drops have formed? In 1 ml, how many drops do you count? Whether it's 25, 26, right? And then that many drops, right? Then what is the volume for single drop? Do this multiple times. No, still not getting it? Oh, okay. So now you know volume, right? So considering that drop to be spherical, I made that assumption also in the beginning. You assume that to be spherical. I think I said it, right? I hope I have not forgotten that. Right? So assuming that to be spherical, then you can do that calculation. Like that, okay. You forgot that, maybe. Fine, that's okay. Okay. So coming back to systematic now. You can keep the syringe down right now. I mean, you can try that later. But it's not a gift for you. I mean, I will need it back. So the same influence affects the result for each of the repeated measurements, but you may not be able to tell. Right? You learn nothing extra by repeating the measurements. Like the example that I just discussed in the previous session, the scale. You keep measuring it without looking at that 0 there. You'll get the same thing. You do it 10 times, you will still get the same thing. Unless somebody comes and tells you or you realize yourself that no, there is a problem with the scale, there is a systematic shift in that, nobody is going to save you from that. Inverse square law, the first slide that I showed you, I versus 1 by d square, right? Intensity versus or current versus 1 by d square graph. Generally, you struggle to get a straight line graph in that. Do you know the reason? The source that you use, okay, you assume for inverse square law, you assume that to be a point source. But do you use a point source? No. You use a filament bulb or a LED, right? Any of these two, right? If you use that, then maybe when you go away from that bulb, maybe 10 centimeter or so, then you start getting a straight line graph, right? You must have seen that. ऐसे फिर बाद में वो straight line होता है. If that is the systematic shift of 10 centimeter, if I plot the graph of 1 upon root I versus d, right, don't you think I will get rid of that? Instead of plotting I versus 1 by d square, I plot 1 upon root I versus d. I get a beautiful graph. Try this. Try this. With that graph not passing through origin, but because there is this 10 centimeter shift. It's a beautiful experiment to understand the role of systematic shift. Okay, try that. Okay. Fine. So what are some of the systematic uncertainties? Zero errors that we all know in screw gauges, vernier calipers, right? Faulty wooden scales, dark reading. What is a dark reading? Any idea? Say it loudly. Acha, something else. Okay. Anybody who knows dark, what is a dark reading? Nobody? Okay. So you are in, say, doing some experiment with LED. Again, say inverse square law. Let's see. LED and a photodiode. You are aware of these two terms? LED and a photodiode. How many of you do not know what a photodiode is? Raise your hands. Everybody knows? Great. Okay. So you have a LED and a photodiode, right? LED is not on, it's off. You still get, and you are doing this experiment on this first table here, right? You still get some reading in the multimeter connected to a photodiode. Why? Exactly. So you expected a complete darkness, but you still get a reading, that is dark reading. What will you do now? You will record that reading somewhere, that this is the reading that I am getting when the LED is off or that bulb is off. And when I switch it on, that constant reading will get added every time in that. So if you subtract it from every reading, you are taking care of that systematic shift. Right? That is dark reading. Is it clear? Dark reading, right? Okay. Familiar with this? You know, that there is a voltmeter with a pointer supposed to be in this position, but most of the times 99% you get something like this. What do? You just slap it so that it comes to 0. No? That's what you do, right? Okay. But there is a screw here. You can just turn it and then bring it to 0. But even if you don't do that, that is the extra reading that you are getting when there is no voltage across it. Right? So when you connect it in the circuit, if that is the condition, then you note it down somewhere and you have to subtract that one division from every reading that you get. So systematic shifts are like that. You need to know what is the problem. And that's why they are very dangerous. Very dangerous. If they just lie there, only God can save you. Even God will not save you. So there is there in that, right? Okay. Okay. Have you seen this kind of a table somewhere? Loading, unloading? Oh, you have? Oh, great. So cantilever, right? You take this loading as well as unloading. Q? Why? And don't tell me it's written in the manual, so we have to take it. Okay. So, see, bending is a very slow process, right? For example, if this is the wooden scale, I attach a mass here, right? It's a very slow process. These layers are going to get stretched. These layers are going to get compressed, right? You will have to really wait very long till it comes to this level. You don't have so much of time, right? So you have taken reading when it's here, right? While unloading, when you have unloaded for the same mass, right? You are supposed to, wait till this. You don't have time. You have taken already reading here, right? If you take mean of that, you expect that that will be the equilibrium reading. That's why loading and unloading, right? So if you really look at that, there will be a difference between this loading and unloading reading, which you are supposed to get, right? You are supposed to get that, right? So if you take average of that, you will expect that you have reached the equilibrium value of the data, right? Okay, fine. So this type of error is basically called as error due to hysteresis, like laziness. Right? What is hysteresis? Laziness, right? That scale takes so long to come there. You don't have time to wait till that long. You just take the reading somewhere else. Right? Okay, let's try to understand these two words. Okay, you know this game, Three Idiots, right? Okay, so or bow arrow, right? In bow and arrow, you are supposed to hit the bullseye every time. This is accurate and precise. This is precise, not accurate. There is something happening with the arrow, right? That I'm trying to hit the bullseye, but maybe there is some kind of air drag, okay, or maybe the arrows themselves are not good. Okay, there is some kind of a different mass distribution of that arrow. So even if I'm aiming the bullseye, it's going there systematically, right? Systematically away from the bullseye. That's systematic shift. Right? So these are the systematic uncertainties present in that. Right? Not precise, all over the bullseye. Can I call it as accurate? Yes, to some level, because there is a randomness involved there. Right? This one, not accurate, not precise. Right? Now the picture is very nice as long as you can see where the bullseye is. That means where the true value is. I remove that. I mean, come on. This is less random uncertainty, less random uncertainty, more random uncertainty. That's all. That's all I can say. Because I really do not know what the true value is, and that is the real life. That is the real life. You do not know what the true value is, so you do not know whether things have been really away from that bullseye or not. Unless somebody comes and tells you, please look at your apparatus, there is a systematic shift in your data because of so and so problem, right? So, in other words, what happened? Oops. Okay. In other words, if you have less random uncertainty present in your data, if you can identify possible sources of systematic uncertainty and if you can take care of it, then you will proceed towards more accurate best value. Right? So, look for possible systematic uncertainty in your data. So, anytime in your life, whenever you come across any new experiment, always try to understand if there is any kind of a systematic uncertainty popping up in your data, right? If it is, take care of it. And this will be very much evident when you are expecting a certain result, when you are expecting a certain graph, and then you are not getting it. As inverse square law, right? You are expecting a beautiful straight line, but you are not getting it. Look if there is any problem with it. Right? So any experiment, make sure physics never goes wrong. These two culprits always try to spoil your result. Random and systematic. Right? Look for them. Okay. Okay, so if systematic uncertainty is there, and if you can spot and identify it, you can take care of it. And if it's random, you can calculate it. Right? So, how much uncertainty can we tolerate in our measurement? Something like one statement that I made in my last session, 1%. Who gave you this answer? 1%. Right? Why 1%? Okay. So ask these questions. Right? Why 1%? Right? Let's try to understand. So something known as sensitivity analysis will help you answer this. What do you mean by sensitivity analysis? Try to come up with what are the different possible measurements that you are doing in your experiment. Let me again take help of simple pendulum, right? So this is your formula, right? So what are the measurements that you do? L and T, okay? You can write down the relative uncertainty, quite easy to do that, right? So what are the two measurements that I'm doing? Length and time. How do I measure length? So with 0.1 centimeter, and typically length measurements about 10 centimeter, because below 10 centimeter, I cannot measure time. You know, today also, like you go to your room, hang something, I mean, object, not your room partner, okay? Okay. Hang something and try to measure time for that. I mean, you will be surprised to see below 10 centimeter, you just cannot measure that. It's so fast. Right? So minimum thing is 10 centimeter, right? If that is the thing, what is the uncertainty? It is 1%. Right? So one parameter, I know the maximum thing that I can do is 1%. Right? Then, if that is 1%, let's equate the second quantity also to 1%. Because then measuring the second quantity very nicely doesn't make any sense to me. Because when I add these two, this 1% is going to dominate. Unless I make some efforts to make those measurements really nice, right? I don't start with say 10 centimeter, I start with say maybe 50 centimeter and above. Yes, then I will go for a better uncertainty in that, right? So if that is 1%, then I can equate 2 into delta t by t equal to 1 by 100. Delta t by t will be 1 by 200. So the time measured should be at least 2 seconds. But we measure, at least 10 seconds and more. I think we have discussed that in the previous slides, right? So that is something that guides you, that what is that parameter in your experiment which is going to give rise to maximum uncertainty in the measurement. And then accordingly you try to adjust the other measurements. Making very nice measurements in other parameters and very bad in this is not going to serve your purpose. So your basic idea will be, if you can get this quantity which is giving you the largest uncertainty, can you reduce that? Right? Can you reduce that? Okay. That's how any experiment uncertainty is decided. So 1% is generally a number which actually comes from this logic. So tomorrow you come up with some measurement which is better than that, fine. I will go ahead with 0.1%, no problem at all. But then try to make sure that all other measurements can be done with 0.1% or less, not more certainly. Okay, that is how this one number comes, 1%. This is not again a very sacred number talk about. Okay. Okay. So this is the formula that I think you have been very much aware of, right? If you make multiple measurements, like you have a wire and then you measure it multiple times, then you use this formula. You take mean of that, then subtract every value from that mean, right? Square it, add the whole thing, and divide by n into n minus 1, and you will get standard answer in that, right? And when do you do this when do you use this formula? When you are measuring the same quantity every now and then, right? Another example I hope I have, say Maxwell bridge. Every time I try to imbalance my bridge and then adjust some other component in that bridge and try to get the balancing condition, and finally again calculate L. Again imbalance it, balance it, get L. So I do it so many times, right? So you can use that formula there, right? Okay, there is something known as range method, or what we call as a shortcut method, but fine. Time measurement. So if you have say 3 readings, T1, T2, T3, right? Then you can get delta T by T max minus T minimum divided by 2. Right? Maximum minus minimum divided by 2. And that will directly give delta T. Right? So for example, in this case, it will be around 0.09 second. Right? And now this method is very much applicable for very small sample sizes, something like 3 or 4. And generally for all your time measurements, you don't do more than 3. Right? So this is like, you still apply that formula of say Ti minus T bar whole square summation upon n, the same thing will come out. Okay, you can try that sometime, right? Just maybe measure some time and then just measure it 3 times and use that formula, and this, you should be getting it almost the same. Okay. Now uncertainty in the slope, right? The logic is same. What do you mean by uncertainty in the slope? So this is called as eyeballing method. Okay, estimation, right? By what magnitude my best fit line can deviate, right? Because on a given day, if I give you a set of points, right, you will get me a best fit, right? Tomorrow I give you the same set of data points. Are you sure that you will get the same slope value? Unless you try to influence yourself, नहीं यही 2 points है उसमें से मैं draw करूँ, नहीं, right? A completely random situation for you. Okay, I mean, you wake up in the morning, I give you the same data set. You again wake up in the next morning, I give you the same data set, right? You might get some kind of a deviation in that, drawing a best fit. So what is the maximum and minimum deviation that I can get in the best fit? Okay, that will give you the uncertainty in the slope value. How to do that? So this is the line, right? Get center of the graph, right? Draw another line, okay, with maximum deviation, but with first criteria of best fit satisfied, not the second criteria. What is the first criteria? Equal number of points on the both sides, right? So you can go bad on the upper side, you can go bad on the lower side, right? Get these two lines, S1 and S2, and get delta S by S. So again, your delta S is nothing but range method, S1 difference S2 by 2, because maximum minus the minimum divided by 2. Right? Again, this is an estimation. If you really want to do uncertainty in the slope, there are formulae available, which is dictated by your least square fit method. Right? If you are interested, I can just give you those formulae. But very sure, if you are doing it manually, you will make mistakes, right? But if you have your laptops and everything, I mean, come on, I mean, you can just do it within no time, right? But this is one way of getting uncertainty when you do not have your laptops, you do not have those least square fit formulae, and you want to estimate what can be your maximum and minimum deviation in your best fit lines, right? Of course, one needs to have a practice for doing that. When we conduct workshops for Olympia students or something, like we do give them this practice, maybe at least 10 to 12 graphs. So you are used to developing that kind of a vision to see what is the maximum minimum thing. Okay. So if I have a experiment, okay, so like a final experiment now, and then you have y equal to say mgl upon pi r square L. So this is like Searle's method, in which what you do, you have a wire here, you stretch it by attaching certain weights, right? So as you go on putting those weights in that hanger, it will stretch, right? And then you have some kind of a standard kept here, main scale, vernier scale reading. So whatever the extension, you can measure it against that. This is the traditional apparatus of Searle's method, right? So what are the things that I'm measuring here? So m is the mass attached, capital L is the original length of the wire, small r is the radius of the wire, right? And small l is the extension measured. Is that clear? So now I'm going to plot a graph between L and M, small l and capital M, extension versus mass. That's logical. Other things I'm just going to measure beforehand. Is that okay? Yeah, okay. So the slope will be delta L by delta M, right? Some length upon mass now. Okay. So just by looking at the formula, I can write down the uncertainty for the standard uncertainty. This is like RMS value, right? So delta L upon L square plus twice delta R upon Y, twice, because this is R square here, right? R square. And then delta slope by slope, because I am plotting graph between L and M, right? So that I will get it from the uncertainty in the slope. And this, I can just, I know delta R is the least count, right? Radius of the wire. Okay. How do I get this? Of course, I don't have to convince you about this thing, but let me just go through it. So the uncertainty in Y will be due to three parameters: measurement of small r, measurement of capital L, and then the slope, right? I divided everything by this Y. And then if I differentiate this with respect to L, it is like I'm del Y by del L into delta L. So that will come something like this. Then I divide this by the Y value, and I should land up again in delta L by L. Of course, I don't have to do this every time. I just look at the equation, and I can, if it is just like capital L, I will just write it as delta L by L. If it is R square, I will just write twice delta R upon R. Even if it's in the denominator, look at this, what happens. This will be something like minus 2 upon R cube into delta R. You divide it by Y again, and you have minus 2 delta R upon R. And that minus sign goes away when you square it. So uncertainties are always getting added. You cannot subtract uncertainty, right? Okay. And then with respect to slope, you again get delta slope by slope over here. Same thing, right? Of course, during the lab sessions also, whenever you have certain formulas, we will help you to come up with those formulas. So, I mean, don't have to be so much worried about that. How do I come up with that? But then I do not know in your colleges whether you calculate standard uncertainty or maximum possible uncertainty. The difference is here I am squaring each of this term. If I am calculating maximum possible, it will be just delta L upon L plus twice delta R upon R plus delta slope upon slope. That is the worst case relative uncertainty, right? or maximum possible. I mean, it has different names. Right? I think you calculate worst case. Yeah, you do not calculate standard density, right? Okay, fine. Anything. I think that's all. I have 14 minutes still remaining this. Let me take you through. Did someone clap? Good. My God, people are looking for that. Yes. Okay. Fine. Who is the best? Not among any of these. I mean, this is not a feedback session now. No. This is just the first session today. Okay. So this is some activity that I normally give it to the students: simple pendulum, bar pendulum, or Cater's pendulum. Right. So as I told you, Cater pendulum gives you a better value. Okay, for an obvious reason, because in simple pendulum, you have this L and T measurement, right? And when you have this kind of measurement, if you really start plotting error bars, which I did not discuss because this is the first day of the camp, I don't want you to bombard with many things. But are you aware of this convention called error bars? No? Okay, let me just show you here. Suppose if I have a graph of L and T square, right? Say centimeter second square, right? One point that I have plotted here, this is uncertain by certain amount, right? On x-axis as well as on y-axis, right? How much is it? How much is it uncertain here? Least count of my measuring instrument, which is 0.1 centimeter. Yeah. So I will draw 0.1 centimeter here and 0.1 centimeter here. So what does that mean? My point can lie anywhere there, right? Similarly, for this y-axis, what will it be? Will it be just delta t or something else? Get that? It won't be just delta t. And that's the problem. Because if this is the uncertainty in this point here, the next point, it will be still larger. Because my t is increasing. And that's why it's not such a good experiment to get value of g. Right? Second, bar pendulum. Which graph will I plot there? Can you just linearize it quickly? K is a constant. Right? Don't worry about that. Can you quickly linearize it and tell me which graph will you plot? Yeah, I'll just maybe give some time to others and I want a linear graph. And I just saw you. Should I show it? Same thing. Yeah. So I'm plotting a graph of LT square versus L square, right? Now remember, it's square. It's square, right? A small systematic shift in measurement of L, okay, will give me trouble in the final value of G, because it's L square now. It's not just L, and I cannot modify. I just cannot do anything with this whole equation. I cannot have any jugglery so that I have L here and then something else there. No, I cannot do that. And from where does this problem actually arise? In a bar pendulum, you have holes here. Right? And if this is supposed to be CG, if you make a mistake even by 0.5 centimeter in that, your G value is going to get spoiled. It's so sensitive. It's L square here and LT square there. It's where slope changes, right? But if you can take care of that problem, you get beautiful value of G. Beautiful value of G, right? Okay. So that's what I mean. This is not a bad experiment, right? But then you should be aware of the shifts that you might be coming across. Right? If you are aware of that, great. Even this will give you a beautiful value of G. Okay. And this is Ketter's pendulum, right? So the idea in which that you do is, this is like one knife edge here, another knife edge there. It is not normally kept in horizontal position. It is generally kept vertical position, right? And then you oscillate it. Right? So you oscillate it from one knife edge, right? See what is time T1. Then you invert it, see what is time T2. And then you are going to move these masses, right, in such a way, these masses in such a way that T1 and T2 becomes equal, almost equal. And this is, you can achieve it in different ways, right? One of the ways, I will just show you the graph here. You vary T1 with respect to L. L is nothing but the distance between knife edges, right? That this is your T1, this is your T2. The place where they meet, okay, that is the equivalent length of the simple pendulum. Okay, and just use the formula of simple pendulum and get value of G. So the determination of this point is done so carefully in that experiment that you just cannot, deviate from a good value of G. Right? And that is the place where, when you determine this T1 and T2 to be exactly same, right? This one, right? That is the place where you take 100 oscillations. Why? Because the moment I take more number of oscillations, I modify my least count. I can go up to maybe 4 decimal place and see whether T1 and T2 are same or different. Right? And that's the beauty of this experiment, right? So the answer is, Ketter's pendulum is the best. Right? This is my personal favorite experiment. Right? That's all. Thank you. I'm done with it. Yeah. So there's still 6 minutes remaining. If you have any questions or anything, or you want to do that activity or something, please let me know. There is another activity that I normally do, but did not do this time. Measuring something, right? So like the same series that I have given you, right? So can you get value of G? Okay, can you get value of G by just making a water drop fall from the syringe to the ground? Okay, something that you need to have with you is a simple stopwatch and some measuring tape. That's all. That's all. You want to try? Or tired? Maybe that's fine. No issues. Yeah, tell me, please. Yes, so you will be 0. Yeah. Mm-hmm. No, because then you will complicate your life. Then you have to measure, what is the change of that potential energy into kinetic. Yeah, exactly. But okay, fine. With the same method that you have, can I really devise an experiment to calculate or say measure the velocity? Can I do that? G तो find out करना है. Of course, but my final aim is G. Yeah, but then another problem that you will have, what value of V are you talking about? Because this is an accelerated motion. So yeah, things will be a bit tough in that case. Any other method? Just using S equal to ut plus half gt square. Discuss with your person sitting next to you if that person is awake.
It thought it would be a fun thing.
Yeah, I think you can make a comment on that.
We have 2 minutes.
Yeah. Okay. Any answers on this? No, not this first. Let's discuss this, and then I think there's a fun thing on that. So you have to form a drop and make it fall. Okay. And then measure the period. I mean the time, sorry. Time for fall. From there to there. No, just single drop. Oh, but the moment it leaves the syringe, how does it matter? उसको क्या हो रहा है वहाँ पे? Simple.
Atmospheric pressure.
Yeah.
Atmospheric pressure difference. And there.
No, she is trying to say that when you press it, no, if you apply more pressure or if you apply less pressure, what will happen? But then, I mean, the moment it leaves, I mean, it has no history. I mean, वो गया अपने हिस्से. So what are the things that you will like to do? Come on. This is the last question and then I will leave you. Come on. I know it's the first day, you're tired. A bit? No? Yes? No? I think the evening session is just a social introduction. 6 to 7. No, now 6 to 7. You are aware of the timetable, right? So the next session is at 6 o'clock, sir? Next session is 6 o'clock. So it's the next session. Session. Yeah, 6 to 7 is the introduction. Yeah, then 8:30 again you have to come back here and there will be another session. Yeah, 6 to 7 is also here, right? Okay, before we leave, can I have some answers from you? You just have to make that drop fall, measure it. Do you find any problems with that? No? Yeah, neglect air resistance. Don't no stand below the air conditioner. That's the only thing. Yeah, obviously. You're right. Can someone just show me one data? Forget about the length measurement, time measurement. You all have mobiles. Take out your mobiles, take out the stopwatch. Oh, is it over? Oh, I've just crossed my time. But fine, can we just have 5 minutes?
I mean, it has t square, so
Sorry?
it has t square, gt square, so the square might be a problem. Systematically,
You measure it. Just measure it. From whatever height that you are measuring, just measure it. Yeah, I think your partner is trying to show you something.
फिर यहाँ से कर अपन नीचे गिराते हैं.
Take the same time. Distance.
इधर से नीचे गिराना.
Yeah. Yes. Very good.
Sorry.
Is it that all people are finding the same problem as she just mentioned?
In this case, our response time could give us a problem.
Are you really finding the same thing? Solution? Problem तो सबने बताया. How strong are these tables? Does that give you a clue? But fine, I will not like to test that. Okay. But if you allowed, you can just maybe go on the first floor and just make a drop fall. The moment you increase the length scale, right, you can measure that time effectively. What you people are trying to do is, यहाँ पे रखा है. No, you will not get the answer. That is one. Second thing, a beautiful method used by one of the student in Ratnagiri, Maharashtra, undergraduate college again. There were two people. One student had this syringe in his hand, and then the other student had a stopwatch. Okay. The moment this student made that drop fall, okay, he started the stopwatch, and for the second one, he just moved his leg forward, and then the drop fall fell on his thumb. Right? So he used two different sensors. The problem is we are just using one sensor. यहाँ पे वो यहाँ से यहाँ जाने तक हो गया. But if you use these two sensors, एक यहाँ से और एक जब भी गिरा तभी, right? Beautiful way, right? Sorry? Yeah. Okay. Now, if you take a video, what all things that you really need to consider? There is a possible way of doing that. You need to take a video. Can you take a video with this? Water doesn't have any color. So when you try to record it, you have to adjust your background such a way that you see the drop falling. Right? So you can add some color in that and do that. Okay. And then you have to be at a proper distance to record the video with a scale in the background or some known object. Right? And then you can just put that video on your computer and play it. Sorry? Yeah, yeah, that's right. Okay, so that's the activity. So I think thank you very much for your patience. I'm done with my 2 sessions. I hope I could pass on few things to you, and we'll meet in the lab on 18th morning. And I think you will have a lot of fun. I think PK has also beautiful experiments. And Ranjini, I think she has left maybe for today. And so there are 4 experiments. So hopefully you will enjoy them, and you'll be more patient enough to take the data in some cases, and have fun. Thank you so much. Thank you.